In many applications in quantum information, we assume pure quantum states. But it's also possible for a quantum state to be not entirely pure. This can happen when a qubit is not perfectly isolated from its environment. In that case, it will experience decoherence, which is the loss of quantum superposition. Whenever a state is no longer pure, we call it a mixed state. In this video, I will explain what the difference is between mixed and pure states and how we can represent all states with a density matrix. The difference between a pure and a mixed state is that the pure state can always be written as a single ket vector, and a mixed state cannot. A mixed state is a statistical ensemble of multiple pure quantum states, each having a certain classical probability of occurrence. So how do we write this down? This is where the density matrix comes in. The density matrix is a very inclusive approach to writing down any quantum state, either pure or mixed. For a pure state, we compose the density matrix as the outer product of a state with itself. So rho equals ket psi, bra psi. If we have a pure superposition state, psi equals alpha 0 plus beta 1, the density matrix will be the vector multiplication of the row vector alpha beta and the column vector alpha star beta star, where the stars denote the complex conjugate. To quickly see if a state is properly normalized or not, one can compute the trace of the density matrix. The trace is the sum of all the diagonal elements in a matrix. The density matrix only represents a valid quantum state if the trace equals 1. In our example, the trace is the absolute value of alpha squared plus the absolute value of beta squared. And we know from the Born rule that this is indeed equal to 1. What would the density matrix of a mixed state look like? Let's take a simple example. Suppose we toss a coin, and each time the coin shows heads, we prepare a qubit as 0, and each time we throw tails, the qubit will be prepared in the 1 state. Now there's nothing quantum about throwing a coin, so we cannot write the quantum state as a superposition of the 0 and 1 state. We should write it in a more elaborate way. Psi equals ket 0 50% of the times, and ket 1 50% of the times. So the state is a statistical ensemble of the pure states 0 and 1. We can write this more conveniently with the density matrix. To compose the density matrix rho, we must sum over all pure states psi k in the statistical ensemble, multiplied by their probabilities pk. For this example, the contributions to the sum would be 0.500 and 0.511. If we sum this up, we get the following matrix, and calculating the trace, we can see that this is a normalized quantum state. We can recognize that this particular density matrix is half of the identity matrix. This is a special state called the maximally mixed state. Now we can observe the main difference between the density matrices of mixed states and pure states. We can see that the density matrix of the maximally mixed state has no off-diagonal elements. As a rule of thumb, we can say the bigger the off-diagonal elements of the density matrix, the purer a state is. There is a more mathematical way to formulate this. The purity of a quantum state is defined as the trace of the squared density matrix. So purity is trace rho squared. The purity for a maximally mixed state is 0.5, and for a pure state, it's 1. How do we visualize the mixed state on the Bloch sphere? Remember that pure states are vectors with length 1, which is why we could represent them on a sphere with radius 1. A mixed state is an ensemble of pure states, all happening with a certain probability. We can represent a mixed state in the Bloch sphere by multiplying the pure state vectors from the ensemble with their probability and adding them up. The resulting state vector will then be in the interior of the Bloch sphere, so its length will be shorter than 1. For example, if we have a 50% 0 and 50% plus state, the vector in the Bloch sphere would be simply the addition of 0.5 times the 0 vector and 0.5 times the plus vector. Another example is the maximally mixed state, where we add up 0.50 and 0.51. Adding the vectors will lead to 0, so the Bloch vector of the maximally mixed state is just a dot at the origin of the Bloch sphere. We see that a Bloch vector of a mixed state has a length in between 0 for the maximally mixed state and 1 for the pure state.